Hi, hello everyone, and my name is Edagel de JESUS-NEGRON, and I will be guiding and doing a little walkthrough video for the shortest path routing project, um, and talking a little bit about the implementation of the shortest path algorithm using Python, using the Jupyter notebook for this implementation, and I'm going to be diving a little bit before into discussing the background and significance of the shortest path routing problem, because this is a crucial challenge in areas of telecommunication, transportation, and logistics. And its core, it involves finding the least costly route between 2 points in a network, optimizing for factors such as distance, time, or expense. And the objective for this, at least for my implementation of the problem, is to implement the Dijkstra algorithm to solve this problem and validate the solution with real-world inspired test cases provided by the professor to make sure it's working properly and look for and see the implementation. So to solve this problem, we use graphs, which is a fundamental data structure in computer science. The graph consists of nodes, or also called vertices, and edges, which may carry weights representing costs or distances. In our case, the graph represents a network of the states of the United States, which is the first part here on the initialization of the network. And then we're going to represent where the nodes are states like New York, Texas, Minnesota, and many others. And the edges are the distances between them. The shortest path routing problem involves finding the least costly route between the two nodes in this whole graph. This concept has applications in GPS navigation, networks, routings, and it could be also used for many other uses and applications. So for this project in specific, I used the Dijkstra algorithm, one of the most efficient algorithms for graphs with non-negative weights. It works by iteratively selecting the nodes within the smallest tentative distance, updating the distances of its neighbor, and marking nodes as visited until the shortest path is determined. So I use the Dijkstra because of the efficiency. Efficiency is the key reason of why I selected this algorithm, because it can handle graphs like ours effectively. And with a binary heap implementation, its time complexity is O, V plus E log V, where V is the number of vertices and E is the number of edges. This makes the algorithm an ideal choice for scenarios where we prioritize speed and accuracy in routing decisions. So for the code, we first initialize the graph with all the information provided by the professor, and then we make the calculation for the shortest path, which is this part right here. So this function implements the Dijkstra logic. It initializes distances to infinity and uses a priority queue to select the nearest unvisited node and updates the distance for its neighbors. So this ensures the shortest path from the source to the destination and is computed efficiently. So for the testing, we did the ones that we are required for this project, which are the NY to CA2, WA to GA, and CA1 to NJ. These cases will show the availability to handle the diverse paths in the network. So once this is run, we see that the elapsed time route for the New York to CA2 is going to be 39 microseconds, and the shortest distance from NY to CA2 is going to be NY, DC, TX, and CA2. And for the elapsed time for the route to WA to GA, it's going to be 28.38 microseconds, with the shortest path distance from WA to GA, being WA, Illinois, PA, and GA. And for the elapsed time route for CA1 to NJ, it's going to be 27.1 microseconds, and the shortest distance from CA1 to NJ, 3450, and the path from CA1 to NJ is going to be CA1, UTMI, and NJ. So let's revisit the big O notation complexity for the Dijkstra algorithm. When implemented with a binary heap, the complexity is going to be O, like I mentioned before, V plus E log V. Each node insertion or distance update in the heap takes logarithmic time, ensuring the algorithm scales effectively with larger networks. For a graph, this means that we can expand the number of nodes or edges. The algorithm remains computationally manageable. So, in conclusion, this project not only demonstrates the theoretical foundation of the shortest path algorithms, but also highlights the practical application for these algorithms also. The algorithm used proved to be efficient and reliable for our test cases, and showcasing its value in solving real-world routing problems. So, thank you very much for watching the video, and thank you. See you next time.